Hello everyone and welcome back to Sustainable Solutions Lab. I'm Milad, and in this video we are diving into a foundational chapter by Adisa Azapagic titled Environmental System Analysis from the Handbook of Environmental Engineering. This chapter is a key starting point for anyone serious about sustainability science, engineering decision-making and policy evaluation. It introduces a suite of methods that help us understand and improve the environmental performance of systems, from products and industries to entire economies. Let's break it down. First question is this: why environmental systems analysis, ESA? The chapter opens by emphasizing something we all feel, that today's challenges like climate change, resource scarcity, and unsustainable consumption require more than piecemeal solutions. Engineers, scientists, and decision makers are expected to contribute to sustainability by designing technologies and services that are economically viable, environmentally sound, and socially just. But here is the problem. How do we measure sustainability? What tool do we use judge if one system is better than another? That's where environmental system analysis, or ESA, comes in. ESA is not one tool, it's an entire toolkit of quantitative and qualitative methods that help assess the environmental and often social and economic implications of human activities. What's powerful about ESA is that it takes a system approach, recognizing that you cannot evaluate one part of a system without understanding its connections to the whole. Now, let's look at the main tools Azapagic outlines. I'll explain each one briefly and tell you when and why it's used. First is energy and exergy analysis. These are some of the oldest tools in the ESA toolbox. Energy analysis looks at how much energy a system consumes and how efficiently it uses it. Exergy analysis goes further. It asks how useful that energy actually is. Think of energy as quantity and exergy as quality. Exergy tells us how much work a system could ideally do before it reaches equilibrium with the environment. It's more precise but harder to apply, especially in non-energy systems. Second one is material and substance flow analysis, MFA and SFA. These methods track the flow of materials and substances like aluminum, nitrogen, and uranium through a region, economy, or supply chain. MFA is great for identifying resource bottlenecks and waste hotspots. SFA zooms in on specific pollutants or chemicals and is often used in environmental policy and pollution control. They are both grounded in mass balance. What goes in must come out or accumulate somewhere. Third one is environmental risk assessment, ERA. ERA looks at the potential harm that chemicals, industrial processes, or technologies can pose to humans or the environment. It includes steps like hazard identifications, dose response assessment, and risk characterization. This is especially useful for compliance with regulations, but also for identifying areas where innovation can reduce risk. Four is environmental management systems, EMS. You may have heard of ISO 40001. That's a type of EMS. It's a structured approach to reducing an organization's environmental impact. It follows a plan to check act cycle and emphasizes continuous improvement based on measurable data. 5 is environmental input-output analysis, or EIOA. EIOA connects environmental impacts to economic activities. For example, how much carbon dioxide is linked to the production of goods in the transport sector. It's often used at national or sectoral levels, but it has limitations. It relies on aggregated data, assumes uniform production methods, and isn't great for tracking product level changes. 6 is life cycle assessments, LCA. This is the most comprehensive ESA method and probably the most widely used. LCA looks at the full environmental impact of product or activity from cradle to grave, from raw materials extractions to manufacturing, use, and disposal. It includes goal and scope definition, inventory analysis, collecting all relevant data, impact assessment, translation emissions into effects like global warming and human toxicity, interpretation, drawing conclusions, and identifying hotspots. LCA is standardized by ISO and supported by powerful databases like CIMAPRO, GABI, and EcoInvent. 7 is life cycle costing, LCC. Think of LCC as the economic cousin of LCA. It tracks the total cost of the product or process over its entire life cycle. It includes both direct costs and sometimes externalities like environmental damage. LCC can be used alongside LCA to evaluate eco-efficiently balancing cost and environmental performance. 8 is social life cycle assessment, S-LCA. It's still emerging. S-LCA evaluating the social and ethical dimensions of a product or process. It considers stakeholders like workers, consumers, local communities, and even value chain partners. Issues like child labor, discrimination, and cultural impact are part of the analysis. Unlike LCA, it relies on both qualitative and quantitative indicators, which makes it powerful but also more subjective and data intensive. 9 is cost-benefit analysis, CBA. CBA is widely used in public policy. It tries to express all benefits and costs, environmental, social, and economic, in monetary terms. It's useful because it gives a single value to compare alternatives, but critics say it oversimplifies, especially when placing dollars value by diversity or human life. So, what do we learn from this chapter? There is no one-size-fits-all tool. Each ESA method has strengths and limitations. We need to choose methods based on the scale, type of system, and sustainability dimension we care about, environmental, economic, or social. In practice, the best assessments often combine multiple tools. For example, using LCA with LCC and S-LCA to provide a well-rounded sustainability analysis. Azapagic reminds us that the goal of ESA isn't just technical. It's about making better decisions in a world facing deep and interlinked sustainability challenges. Whether you are designing a product, planning a city, or setting policy, these tools can help us move from assumptions to evidence, from opinions to informed action. If you are a researcher or professional working in sustainability, you need to be fluent in these tools, not just to run the models, but to interpret and communicated them meaningfully. If you found this video helpful, don't forget to like, share, and subscribe to Sustainable Solutions Lab. I'll see you in the next episode where we continue exploring how to build a more sustainable future through critical thinking and systems insight. Thanks for watching.